Okay, so good morning. So my name is Nicolas Saun. I'm from Open Analytics. And I'm here to present a method called hierarchical non-negative matrix factorization, which we apply to a set of MRI data, medical imaging data, to differentiate brain tumors. So quick overview of the presentation. So the method that we developed is based on non-negative matrix factorization, or in short, NMF. So I'll first tell you a bit what that is and how it can be applied. Oh, sorry. Then I'll tell you a bit about the context in which we use this method, which is multiparametric MRI imaging of brain tumors. Then we'll come to the actual method, hierarchical NMF, and I'll show you how hierarchical NMF works within R. So non-negative matrix factorization, or in short NMF, as the name says, it's a matrix factorization technique. So some of you might be more familiar with principal component analysis. So that's also matrix factorization technique. So basically you put your data into an input matrix, and you're going to decompose that matrix into two factor matrices, W and H. Whereas, for instance, in PCA, you would impose orthogonality of your principal components. Here, the only constraint that you impose is that all the elements of all the matrices are non-negative. Yeah. So it's an unsupervised learning technique, which means that you can apply it without any training data. And as an input, you require a rank R, which basically tells you how many components you're looking for. I don't know why he's always moving forward. But so as an input, you need a rank R, and it's a non-convex problem that we're solving, which means that instead of a global minimum of the objective function, probably you will find a local minimum, and for that you need an initialization. Yeah, sorry? Yeah. No. Yeah. So anyway, as an input, we need the rank R, and we need initial values for the factor matrices. So NMF basically gives you a parse-based representation of the data. So what does that mean? Actually, this constraint of non-negativity applies quite naturally to many applications. So we kind of assume that each data point can be modeled as a weighted sum of the basic components. That's what NMF assumes, and that gives us, in many applications, gives us interpretable results. Applications such as computer vision, chemometrics, document clustering, and so on.
The mouse doesn't work now. Okay. Do you know how to maximize it?
Yeah. You just go to the top of it. Yeah. Oh, thanks. Okay. Okay. So let's try again. So a bit about the application that we were working on. So it's MRI for visualizing brain tumors. So MRI stands for magnetic resonance imaging. And here on the left, you see an example. You see an example of a T1 weighted MRI image. And you see that circular structure there in the image, which is a brain tumor. Actually, it's a grade 4 glioblastoma, which is the most malignant and unfortunately also the most common brain tumor. So when a patient is diagnosed with this lesion, well, it will very likely lead to the patient's death. But what we try to do with clinical treatment is to extend the patient's lifetime and to increase the quality of life. To be able to provide proper clinical treatment, what we need is an accurate delineation of the tumor and its subcompartments. So a brain tumor is not a homogeneous mass. It's actually quite heterogeneous. Various stages of the disease can occur within the same lesion. And basically we want to differentiate mainly three different tissue types within the tumor, which you see there indicated on the right. So the red circular region is the active tumor region. So that's the actual tumor cells, that's the growing part of the tumor. In the core of the tumor in green, you have necrotic tissue. That's actually dead cell tissue. So these were tumor cells that were not supplied with sufficient blood and oxygen supply, and so they basically died. And surrounding the tumor, we have edema, which is fluid, which can increase the pressure within the brain. So based only on this conventional MRI data, it was found that we cannot really give a reliable automatic differentiation of these tumor substructures. So what we do is we consider multiparametric MRI. So that actually means that we have our conventional MRI data, and we're going to include additional MRI modalities, which give us additional information about our brain tumor. So conventional MRI basically gives us information about the tissue structure. And besides that, we also consider perfusion-weighted MRI, which gives us insight into the vascularization within the brain and within the tumor. We include diffusion-weighted MRI, which gives us information about the mobility of the water molecules within the brain. And we consider magnetic resonance spectroscopic imaging. That modality gives us insight on the spatial distribution of metabolites in the brain, so certain chemical components within the brain. So the idea is that we combine all these modalities. So basically for each pixel in our image, we have a set of MRI intensities. And so we have 4 imaging modalities, but for each of them we have several MRI images, in fact. So in total we have 15 MRI features in each voxel. So how does that work now if we want to apply NMF? Yeah.
Ik zie het alleen maar op het scherm hier.
Sorry for that. Apparently there is an issue. There is an automatic timer on all the presentation in all sessions. So, but this should be fixed soon. Yeah.
Yeah, I know where it is. Yes, okay. Yes, okay. Okay.
Okay, so back to the NMF algorithm. So we want to apply that NMF algorithm to our imaging data. So how is that going to look like? So we have to organize our imaging data into the input matrix. So basically we put on the columns the different pixels, and the rows correspond to the different MRI features, the different MRI imaging modalities that we have. So we decompose that matrix into the 2-factor matrices. Each of them have their own specific meaning. So actually, if we look at the columns of the W matrix, each such column basically represents a tissue signature. So on the rows, we have the MRI features again. And basically, we have a representation of one tissue type in each column. It's what we call a source vector. Then if we look at the second matrix, the H matrix, there we have to consider the different rows. So if you look, for instance, at the first row, so here the columns correspond to the pixels again. And so basically here we get the weights of the different tissue sources in each pixel. And so the first row, for instance, gives the weights over all the pixels for the first tissue vector. So basically, we expect to get really interpretable results. And this is, for instance, what the result could look like if we apply NMF on the data for one patient. So here we have analyzed a small region of interest around the brain tumor. Within that region of interest, we found 5 tissue types. So it means we have to apply NMF with the rank 5. And this is what the output could look like. So here on the left, you have the tissue abundances. These are the rows of the H matrix. We can transform them back to the spatial domain. And so each map that you get here is actually a row of that H matrix. And so you basically see the distribution of the different tissue types within the region of interest. And then here on the right, you see the columns of the W matrix. So each curve is one column. And they basically are the tissue signatures in function of the MRI images. So with NMF, we get already quite good results to differentiate our tumor subcompartments. What we were looking for, a method that would do even better, and that's how we came up with hierarchical NMF. So this is the schematic of the algorithm. It might look a bit confusing, but actually it's not so hard to understand it. So basically it consists of 3 levels. The first level, so we have a first level of NMF that we apply, second level of NMF, and in the end we have to recombine the results. And so we start with our input matrix. First we're going to apply a rank 2 NMF. NMF where we look for 2 sources. That also means that we have for each source an abundance map. You see the 2 abundance maps here. And we're going to assign all the pixels within our region of interest to both sides. So the pixels which have a high abundance for this source, they will be assigned to this side. Pixels which have a high abundance for this source will be assigned to that side. And then we're going to apply NMF on these 2 separate groups of the pixels. We're going to apply NMF, and we basically assume that after this first level, each of the 2 sources that we get represents a number of tissue types. So the first source will represent some of the tissue types. So we apply NMF with rank equal to those tissue types, and the same goes for the second source. And then after the second level of NMF, we expect to find our actual tissue signatures. So here we have our tissue signatures, but then we still have to recombine, since we analyzed the pixels of this side and of that side separately. We have to recombine all those sources. We can do that using non-negatively squares fitting, and that will give us the abundance maps of all the tissue types. So just to give you an example of a comparison of single level NMF with hierarchical NMF. So here you see the abundance maps of the pathological tissue types. So this is active tumor, necrosis, and edema. And we need a way to quantify the quality of that result. And for that, we use a manual delineation of these tumor compartments by a radiologist. And we can quantify that in terms of the dye score, which is a measure of the spatial overlap between the manual segmentation and the abundance maps that we get from the NMF methods. And there you see, so for the different tissue types, that HNMF gives higher percentages. Also, if you look at the abundance maps, you can see that HNMF gives more sparse abundance maps. And so the color maps that you see here they are the spectral color maps that I obtained using the color brewer package. So deep blue corresponds to near 0 values. And so you see that here, for instance, for active tumor, you still have light blue in the surrounding healthy region. Is what we call contamination of the pathological sources. And you see that that occurs much less with the HNMF method. So the HNMF package is available on CRAN. It's a plugin, so it's building on the existing NMF package, which is the most commonly used package for performing NMF analysis. Within our HNMF package, we have implemented 2 state-of-the-art NMF algorithms. So we have projected gradient descent NMF and hierarchical alternating least squares NMF. And as I mentioned before, you need an initialization of your factor matrices. So as an initialization method, there is random initialization available, which is most commonly used, but we also provide a successive projection algorithm, which is a more sophisticated initialization algorithm. Besides HNMF, you can also run single level NMF analysis with the package. So just to show you the syntax of the HNMF function itself. So basically you need 2 input parameters. You need an NMF model. And that model is actually an object as it is defined within the NMF package. So it needs to contain your initial values for your factor matrices. And based on the dimensions of those factor matrices, you also automatically obtain the rank of your NMF analysis. And then you need to specify a method, which is the NMF algorithm. So you have the 2 algorithms that we have implemented, but you also have available all the NMF algorithms from the NMF package. So I've been showing it here on an application of medical imaging, but the method is actually generally applicable to any problem where NMF could come in handy. And when would you expect most added value of HNMF over single NMF is in cases where you have so-called low abundance source or sources, which means that one of the sources is only present in a relatively small amount. So for instance, in the context of brain tumors, suppose you have a very small brain tumor, probably HNMF would be better able to detect that than a single level NMF. Another scenario where HNMF gives a lot of advantage is when you have strongly correlating sources. So in this case, that would mean you have tissue types which have very similar tissue signatures in terms of the NMR, in terms of the MRI parameters. And with that, I'd like to thank you for your attention.